So a series is a sequence with plus signs. Just like a sequence, a series can be finite, in this case 2, 4, 6, 8, stopping there. Or a series can be infinite, meaning that you keep adding all of the values together onto infinity. So they follow the same pattern, or they follow a pattern just like a sequence does, but we add the terms. So a finite sequence seems pretty obvious and easy to deal with. A finite sequence would just be a finite set of numbers that I choose to add together. So if I added 2 plus 4, I get 6, plus 6 is 12, plus 8 is 20. The finite sequence, 2, 4, 6, 8 equals 20. This is called a partial sum. And it's partial because in the sequence, it's only part of the infinite sequence. I've only taken a part of it, so the partial sum. And we denote the partial sum using the notation capital S for sum and n, meaning I've gone to the nth term. So in this case, first term, second term, third term, fourth term, I would say that the sum of the first 4 terms equals 20 for this sequence. Excuse me, for this series. So let's do an example of a partial sum. Calculate one. We want to find the 5th partial sum of the series defined by the formula a sub n equals n squared minus 3. And we want to find s sub 5. So a sub 1, let's start there. This is an explicit formula, which means I can just calculate each one. A sub 1 equals 1 squared minus 3, so that's 1 minus 3, negative 2. A sub 2 is 2 squared minus 3, so that's 1. A sub 3 is 3 squared minus 3, so 9 take away 3 is 6. A sub 4 is 4 squared, take away 3. 16 take away 3 is 13. And a sub 5 is 5 squared, take away 3. So that equals 25 take away 3, 22. So the sum of the first 5 elements or terms of the series defined by the formula a sub n equals n squared minus 3 is negative 2 plus 1 plus 6 plus 13 plus 22, which equals 40. So this whole process brings us right to a new form of notation called sigma notation. I'm going to make a correct sigma symbol, and this will be the only time you'll see it from my notes. This is sigma. It is the Greek letter, capital letter for S. S stands for sum, because what we're doing is we're finding the sum of a sequence of numbers. So my sigma, by the way, looks like this. That's what you'll see from now on. And the notation for instructions tell us that we want to add all the elements from n equals 1, being the first term, all the way to the last term, k. In this case, k would equal 5. And then we're given the formula, in this case, n squared minus 3, that produces each element. And these instructions tell us to add plug 1 in for n, and then add to that, plug the next integer up, 2 in for n, then add to that the next integer up, 3 in for n, and so on, right up until we get to put k in for n. and then find the value, the total. So I'm going to use this notation now to do this problem again. The sum, as n values start with 1 and end with 5, right? So a sub 1, a sub n means a sub 1, a sub 2, 3, 4, 5. Of the formula, n squared minus 3 tells me to add 1 squared minus 3, to add 2 squared minus 3, to add 3 squared minus 3, and then 4 squared minus 3, and then 5 squared minus 3. And if I add all of those up, I know I'm going to end up with 40. So if I look at what I have, this is exactly the same thing I did here to find my first term. Then this second term in the addition is exactly what I had here. Third one, exactly what I had here. Fourth one, same as the fourth one here. And then last but not least, the fifth one is the same as the fifth one here. So sigma notation is an instruction to do exactly the same thing that the verbal instructions were given in the first part of the example, but sigma notation is a simpler, believe it or not, simpler way to do the same thing. All right, so let's do a couple more examples. We want to find the sum, and we know it's a sum because we have sigma notation. For n equals 1, starting with n equals 1 to 4, using the formula n squared minus n. All right, so element by element, that's 1 squared minus 1 plus 2 squared minus 2 plus 3 squared minus 3 plus 4 squared minus 4. And I'm going to stop here because that was the last term I want. So 1 minus 1, that's 0. 4 minus 2 is 2, plus 9 minus 3. So even though that seems like a lot of work, it's clearly much less work than this, doing it in the other way, even though sometimes I'll want to do the other way. All right, so let's do another example. This time I want to find the sum for n equals 2. I'm starting with the second term rather than the first term. And I want to go to the fifth term of 3n plus 3 over n. Okay, so let's just start plugging in values. I have 3 times 2 plus 3 over 2 plus 3 times 3 plus 3 over 3 plus 3 times 4 plus 3 over 4 plus, lastly, 3 times 5 plus 3 over 5. All right, so that would be 9 halves plus 12 divided by 3 is 4 plus 15 fourths plus 18 fifths. Find a common denominator and combine all of your terms, and you get 317 over 20, which is approximately equal to 15.85. Okay, one more example. It's a little bit tricky. It stems from a convergent sequence, and so we'll evaluate what happens when you add convergent terms together. N equals 1 to infinity, right? So remember, when we talked about a convergent sequence, we talked about a sequence where the values got closer and closer and closer to some number, which means the impact as you get farther and farther away, as your values on the n-axis approach infinity, the impact of each additional term has very little to the impact of each additional term is very small. And so you will be able to see a number to which this series converges. So let's go ahead and have a peek at that. So we're going to take 3 times 1 over 10 to the n. All right, so from 1 to infinity. So let's just look at a pattern. Let's take enough steps to see a pattern. Our first one is 3 times 1 over 10 to the first power plus 3 times 1 over 10 to the second power is 100 plus 3 times 1 over 10 to the third power, 1,000, and so on. Let's look at where we are. Well, 3 divided by 10 is 0.3, plus 3 divided by 100 is 0.03, plus 3 divided by 1,000, 0.003. So you can see that the 0.03, the 0.003 actually have very little impact and will have less and less impact as I move toward infinity. And so when I sum these values, I end up with 0.3333 on and on and on, which is just 1/3. So the sequence in my last example comes from the series in my last example is the sum of a sequence that converges to the line 1/3.